Hej och välkomna till öppna föreläsning här i Fysikum i Stockholm universitet. Och vi är jätteglada och vi har hon Gudnason med oss här. Han pratar om kosmologi and the pre-moval fireball. Och jag först introducerar Jon. Jon han född och vuxit i Island. Och han flyttade till USA och sen han doktorerat i Princeton universitet, den bästa plats man kan göra det här området, forskningsområdet här. Efter hans doktorexamen har han flyttat till Sverige. Han har blivit en postdoktoral och han fått många individuella forskningsbidrag. Han säger från Sverige och sist har han fått en ERC starting grant. Den här kommer från EU. Han är jättekompetitiv den man kan få. Och det bästa man kan få en unga forskare. Och nu han delar hans tid med Island och sen i Sverige här. Och det kommer ett speciellt idag för öppna föreläsning. Och tack Jon, du kommer hit. Och ja, och tack. Ja,
ja. Hello, everybody. I'm going to talk in English. I hope that's all right with you. I've lived here for 6 or 7 years now, but unfortunately my Swedish language proficiency is not sufficient to talk about this special area. Okay, yeah, so I'm going to talk about cosmology and the primeval fireball. In a journey through cosmic epochs with the universal backlight. I'm going to talk about 3K, which this term here refers to 3 Kelvin. And I'm going to point out that these 3 things are essentially referring to the same phenomenon, which in standard science language is now referred to as the cosmic microwave background. So the cosmic microwave background is the afterglow from a period in the history of the universe when the universe was much hotter and denser than it is now. It is the oldest light in the universe, and we can learn quite a bit about the universe and its evolution by studying this light. But I'm going to start with this question here, and statement, which is that astrophysicists today believe that the universe had some form of a beginning. And the question is, why is that the case? This is a very reasonable question, and it's quite reasonable, especially when you think about the fact that about 100 years ago, the dominant scientific consensus was that the universe is static, that the universe is the way today, the same way it has always been. And key scientific figures, including Albert Einstein in the 1920s, were of this opinion. So, thankfully, there were people that were willing to think a little bit differently and try to poke at this standard model at the time. And one of them was Georges Lemaitre, who's seen here in 1933. He actually first met Einstein in 1927 and pointed out in this first meeting that, in fact, Einstein's theory of general relativity accepted solutions that had the size of the universe essentially evolving in time. In 1927, the first meeting that they had, apparently Einstein was quite dismissive and did not like this idea. Which is kind of strange, given what had been happening in observational astrophysics or cosmology at the time. In 1924, 3 years before their meeting, this was a small article in the New York Times stating that Dr. Hubble, as in Edwin Hubble, confirms views that they are island universes, that these spiral nebulae that we can see with our telescopes are galaxies, and we live in one of those galaxies, but there are millions of galaxies out there. So that's a quote from that news article, and this is a diagram showing us in the Milky Way in a sea of galaxies. And we're starting to realize this view of the universe in 1924. So in the 1920s, we're also developing the field of spectroscopy, which is the ability to discern the colors of electromagnetic radiation. And one of the key figures in that is Vesto Slipher, and he's collaborating, I guess, with Edwin Hubble. And we're starting to see results, scientific results, showing that on average, most of these galaxies, the ones that are pictured here in red, are moving away from us. They're redshifted. So that was a big conundrum at the time. Okay, so one of the hardest things in cosmology is in actually the task of measuring distances, cosmic distances. It's surprising, but it's quite difficult. And one technique that was invented by Henrietta Swan Leavitt, who was working at Harvard at the time, used these types of giant stars that we now refer to as, Cepheid variables. And this is a picture from, or collection of pictures from the Hubble Space Telescope, showing that over the period of a month, some stars actually vary quite a lot in their brightness. And Henrietta was working at Harvard, and she was cataloging of order 2,000 of these Cepheid variables. And through observations of these Cepheid variables, she was able to show that there's a relationship between the brightness of these giant stars and the periodicity, the period with which they would go through that full cycle of being dim and being bright. She was studying these objects in a satellite galaxy to our own called the Small Magellanic Cloud. And we were actually able to measure the distance using a technique called parallax to this cloud quite accurately. And because of that distance estimate and this apparent brightness period relationship that she determined, we actually were able to determine the absolute, the intrinsic luminosity of these objects. And because of that, we now have what we refer to in cosmology as a standard ruler. So, thanks to that technique, we could now map out the distances to all of these nearby galaxies and beyond, and use that information in combination with the spectroscopic data, the radial velocity data, to make what is now one of the most famous equations in astrophysics, the one that we refer to now as the Hubble-Lemaitre law, which states that the velocity with which galaxies tend to be moving away from us is linearly proportional to the distance to the galaxies. And the proportionality constant is this h-naught parameter, the so-called Hubble constant. And so Hubble published this in 1929, and many people, including Einstein, after this publication, basically said goodbye to the static model of the universe and started to subscribe to a model where the universe is actually evolving in time. Right. So we typically measure distances using these standard candles, some kind of calibrated flashlights in the universe, and Cepheid variables are one of those. Another famous examples are so-called Type 1a supernovae. I want to make a slight digression and just point out the fact that not all galaxies are moving away from us. Our closest large galactic neighbor is the Andromeda galaxy, seen here, which happens to be approximately 3 million light years away from us. And it's moving at about 300 kilometers a second in our direction, and in about 5 billion years it will collide with our own Milky Way galaxy. I also want to point out that, so we have these standard candles that we refer to as Type 1a supernovae. These supernovae are a specific category of exploding stars. We know of somewhere between 4 and 7 exploding stars in our own Milky Way galaxy in the last 2,000 years. One of the most well-known is typically referred to now as the Crab Nebula. But the more technical name is SN 1054. So when this thing went off in year 1054, it was visible to the naked eye in broad daylight for 23 days. It was 4 times brighter than Venus at peak brightness. And what you can see in this image is the stellar remnant, all of the stuff that the star and the explosion shoots out into the intergalactic medium. And I'm going to talk a little bit more about this stuff that's being shot out in every direction. In fact, we actually have really cool pictures of this thing that lives at the center of this explosive crater, this neutron star here, which is essentially still sending out gas today. These are images from the Hubble Space Telescope. Okay, but back to this picture of cosmic expansion. So you can build a model of the universe where you place galaxies on a regular Cartesian grid, like the one I'm showing here. And if this model of the universe that is expanding is correct, and if our assumptions that we as observers of the universe are not in a privileged point, this is sort of a phenomenon that we refer to, or concept that we refer to as the Copernican or cosmological principle. Our location in the universe is by no means special. If we assume these things, we can assume that at some point in the future, these galaxies will be further away from us. If you had an ability to measure the distance with a physical ruler, the distance would be greater than it was today. But if you turn that picture around, that also implies that at some point earlier in the history of the universe, we were the universe was much tighter, much denser. And so that suggests that the universe was in a very different state many years, billions of years ago. Okay, so this discovery by Hubble and his colleagues in the 1920s is one of the key arguments for this cosmic expansion and the evolution of the universe. I'm now going to talk about another piece of evidence that is somewhat independent, namely the cosmic microwave background. So to tell that story, I want to go back about 240 years to this picture made by William Herschel in 1985. So William Herschel is famous for having discovered the planet Uranus, but he also, 3 years after that famous discovery, he tried to make a map of the galaxy that we live in. And this is his best estimate at showing the azimuthal variation of the galactic plane. And you can see it's quite irregular. You can see that there are valleys and peninsulas in here. And actually, these valleys and peninsulas have something to do with these supernovae explosions. This idea of gas and dust being expelled out into the interstellar medium. And I'll talk more about that in a few minutes. We now have, 240 years later, a much more advanced picture of the galaxy that we live in. These are, this is an image generated by the Gaia satellite, which is a satellite funded by the European Space Agency, launched not many years ago. And you can see here in the visible spectrum an attempt at rendering the entire full sky on a two-dimensional plane. So this is what we refer to as a Mollweide projection. This is the galactic plane. And this thing here is the small Magellanic Cloud, the satellite galaxy that Lea Witt was studying when she was trying to understand the properties of Cepheid variables. Okay, so this is in the visible spectrum, and this is flux or radiation from about 2 billion stars. What happens if you look at different wavelengths? So I've talked about spectroscopy a little bit, so I've already suggested that radiation is composed of multiple colors, and we have the photon or light being in the form of very high energy gamma rays and X-rays and ultraviolet radiation, all the way down to long AM and FM long wavelength radio frequencies. So the visible spectrum lives here at the 400 to 700 nanometers. So what happens if we look at the universe when we've scaled the frequency by a factor of 1,000, or alternatively, we've increased the wavelength by a factor of 1,000. So we're now working in the microwave regime with millimeter wavelengths. So this is the picture of the universe in that case, roughly speaking. And it has a sort of a good link to the first slide where I showed the stamp that was made in Sweden to commemorate the discovery of the cosmic microwave background, the statement 3K. The universe is incredibly uniform in this wavelength range. This is the cosmic microwave background. It's a constant blackbody signal that we see no matter what direction we look into. And it's characterized by a single number, which is the temperature of that radiation field. Okay, so we spoke about static universes. Some of the people in the audience, I'm looking at some that probably don't recognize this, but this is a picture that you would sometimes see when you're trying to tune into a particular television channel, right, on your old CRT television. This is static noise. Turns out that about 1% of the noise in these images that are displaying on our televisions comes from the cosmic microwave background. 1% of the energy that's being shown on that screen is the radiation from a period in the history of the universe when it was much hotter and denser. This is the afterglow of the Big Bang. So I think that's just marvelous. So this was discovered, this so-called cosmic microwave background, or CMB, was discovered in 1964. But there were a few close calls, near misses, things that could have been. So actually, the first scientific publication that sort of talks about the temperature of the universe is published in 1940, as far as I know. And this was based on data that was collected at Mount Wilson Observatory, which is also where Edwin Hubble was doing his research. And they concluded that the temperature of interstellar molecules was of order 2 or 3 Kelvin. When this strange-looking antenna was commissioned in 1961, the engineers did a budget of the different noise components and signal components in the receiver, and they found a discrepancy between that budget and what they actually read out in the receiver. 3 Kelvin discrepancy. A memo in an engineering logbook and nothing else. 4 years later, Penzias and Wilson, two astronomers who are using this receiver in Holmdel in northern New Jersey to do astronomy, to study interstellar molecules, they actually do the same due diligence measurements and find the 3 Kelvin axis. They don't know what's up. They try all sorts of solutions, some which involve dealing with pigeons, etc., but eventually they give up and they phone a friend. That friend lives in central Princeton, or central New Jersey, in Princeton, roughly 42 kilometers away as the pigeon flies. So the leader of that group at Princeton was, at the time, Bob Dickey. And his group was actually in the process of building an antenna, or telescope, that was supposed to detect this primordial fossil radiation from the early universe. So this is at the top of what's now the Geoscience building, David Wilkinson and Peter Roll working on that receiver. So they combined their measurements together with the measurements conducted at Holmdel by Penzias and Wilson, and made this following plot. So we had one data point from the measurement at Bell Labs in Holmdel, and then one measurement from Princeton, 2 data points, and they fit a very complicated function to those 2 data points. That function is the Planck blackbody function, which describes the statistical properties of a type of radiation field. So Jim Peebles made this plot in 1965, I believe. He later received the Nobel Prize for essentially establishing the modern theory of cosmology, the standard model of cosmology. And he gave a presentation in this room 3 years ago, I think in 2019, a wonderful presentation, which I think is available on the physical website. Anyways, so that's the story in 1965. Fast forward about 25 years, and now you have the COBE satellite, 1990, launching, which instead of producing 2 data points with which you can fit that Planck blackbody function, you now have an insane number of data points and a really impressive fit between that curve and the data, suggesting that the temperature of the universe is 2.725 Kelvin. And the error bars are so small that you can't really see them. They're smaller than the thickness of these lines. Yeah, so going back now, it's, we know that the speed of light is finite. So when we're looking into the cosmos, into the universe, we're looking back in time. So what we're seeing when we're detecting this cosmic microwave background radiation are photons that have been traveling through space for essentially the entire age of the universe, for 13.7 billion years. These photons essentially map out a sphere surrounding us on the sky. And we are detecting some of those photons over here in the center of this picture. What we're trying to do in modern-day cosmology with the cosmic microwave background is to use properties of this light to say something about the evolution of the universe. The light serves as a backlight, so this is the universal backlight. It serves as a backlight to events that happen at later times in the history of the universe. For example, we can use the CMB to say something about the birth of the first stars. But we can also try to use something or try to learn something about the events that happen even earlier in the history of the universe by testing the statistical properties of these photons that are arriving to us now. So here's a sort of a nicer picture of that model. We are here, time is going from 0 to roughly 13.7 billion years, which is our estimate for the age of the universe. And here is another depiction of the cosmic microwave background. Okay, so we've been studying this for now almost 60 years. And there are three famous satellites that are deployed: the COBE satellite, which I mentioned earlier, WMAP satellite, which was launched by NASA in 2001, and the Planck satellite, which was launched by ESA in 2009. And we've, by combining data from these satellites, learned a great deal about cosmology, and they've all, each improved on the predecessor. These images that you see here are quite, different from the images that I showed earlier, the black egg-shaped thing, right? There was no interesting stuff in that image. This one is actually quite interesting. The reason for that is now we've actually removed the constant signal on the sky, the 3 Kelvin blackbody radiation field. So what you're left with then is a clear indication that we live in a galaxy. This is the galactic plane. But you can also see these variations in the temperature of the sky. And when you use clever analysis techniques, you actually are able to make estimates, images of these variations across the entire sky. You're essentially able to remove the galaxy. And so this is an image of the so-called cosmic microwave background anisotropies. These are the variations in the temperature of the universe. And now I've changed color scale and units here. This is referred to as microkelvin CMB. These variations are of order 10,000 times smaller than the constant signal. So we have hot spots colored in red, cold spot colored in blue, and these hot and cold spots have a very interesting, or at least we believe they do, have a very interesting origin story. So I'll talk about that in a few minutes. So because of observations of the cosmic microwave background, because of observations across a wide range of frequencies, we've built this model of the evolution of the universe. This is a cartoon. I'm omitting quite a lot of interesting and important time periods, but this model has the beginning of time, Big Bang, followed by a hypothesis period of cosmic inflation, a period during which the size of the universe is inflated by 26 degrees orders of magnitude, so inflated from quantum sizes to something that's actually macroscopic. Roughly 1 second after the start of our stopwatch, we have a period when the neutrinos that are produced in the early universe actually decouple from the rest of the primordial plasma and free stream in every direction. So there's actually a cosmic neutrino background that we think exists. We've actually never detected it, but there are actually experiments trying to do that and working towards that. But that's a different presentation. We then have in the first 3 to 10 minutes a period of nucleosynthesis when the lightest elements in the universe are formed. Hydrogen, helium, lithium, beryllium, and boron. Elements that then end up making the first populations of stars. And then the universe is expanding, it's cooling down as it expands, and eventually it gets cold enough so that the charged particles in this primordial plasma, they actually combine to form uncharged atoms, like deuterium here and hydrogen here, etc. And it turns out that photons, they do not interact as easily with uncharged particles as they do with charged particles. These charged particles over here are interacting quite often with these photons. But at this point in time, 380,000 years after the Big Bang, this recombination or decoupling epoch happens, and the photons that are part of this primordial soup now stream in every direction. So that's the last scattering surface. This is when the CMB photons are emitted, and this is what we're looking at with modern day microwave telescopes. So later in the history of the universe, we have epochs of structure formation, the formation of the first stars and galaxies, etc., etc. And we are somewhere over here in a period, as far as we can tell, in the history of the universe where the energy is dominated by this mysterious thing called dark energy. That's also another talk that I'm not going to mention, or topic that I'm not going to mention in much detail. Okay, so now I'm going to go back again and talk about a discovery that was made by Leverrier. So this person is the person that discovered the planet Neptune in 1846. So he's claimed to have discovered this planet with the point of his pen. So what he did is he used observations of the planet Uranus and essentially Newton's law of gravity to calculate or derive that there must be some mass that's pulling on other planets. And you can see sort of a depiction of that here. So Uranus is discovered in 1782, and it goes around the sun in roughly 80 years. And by the time the Leverrier is starting to work, this planet is being pulled on by a mysterious planet, Neptune. 40 years later, the planet is actually being pulled on in the other direction, and now is slowing down in its orbit around the sun. So these variations in the velocity were what allowed Leverrier to pinpoint the location of a mysterious planet that we now know as being Neptune. And he sent a letter to colleagues in Berlin who apparently were able to detect this planet within a degree of where he calculated it was supposed to be. So that's a triumph of the scientific method, right? It's a really impressive result. But unfortunately, that's not always the case. So I'm going to now talk about something that's closer to us in time, the fact that we can study the rotation velocities of stars in galaxies. And this is a field that in some sense was pioneered by Vera Rubin, who in the 1970s looked at the orbits of stars in different galaxies close by, and she saw that the orbital velocity, shown here on the vertical axis as a function of distance, looked something like this. It went up and then essentially plateaued at roughly 100 kilometers a second. This was strange to scientists at the time because they expected this velocity to sort of taper down and follow a 1 divided by square root r relationship, sort of dropping down as you move out. Essentially what this amounts to is the fact that the galaxies are rotating. This is of course sped up, but the galaxies are rotating faster and in a different way than what we anticipated. So we take this as evidence of a missing mass in these galaxies. This was not the first piece of evidence for missing mass. In fact, in the 1930s, a very interesting character by the name of Fritz Zwicky, who by the way, coined the term supernova, realized that galaxies orbiting galactic, clusters of galaxies were actually orbiting at much higher velocities than we anticipated. So he came up with the word dunkle Materie, and from these observations he concluded that there must be some invisible mass that's pulling on these galaxies and making them spin faster around their center of mass than we expected. So we have multiple pieces of independent observational evidences for this dark matter. Edward Murchell gave a colloquium in this series a few months ago where he talked about strong lensing. And this is a strong lensing system, Apple 370, and you can see these galaxies that have been bent out of shape. And when you do the due diligence on these systems, you arrive at the conclusion that there's some mass here that you can't actually see. It's not emitting radiation, but it must be there because you can see the gravitational lensing effects. When we run high-performance computer simulations using some of the biggest computers in the world that probe this evolution of our universe and the growth of structure, we need to throw into those codes, into those recipes, this mysterious dark matter, this matter that interacts gravitationally but does not interact with radiation, with light, in order to produce images that are consistent with what we see when we look out into the universe. Last but not least, we actually, by looking at these variations in the temperature of the cosmic microwave background, we're able to say something about dark matter as well. In fact, you could argue that this is the strongest piece of evidence for the presence of dark matter. So how does that work? Okay, so now let's talk a little bit about random fluctuations. I mentioned very briefly the concept of cosmic inflation and the beginning of time. You know, we don't know the physical laws that are governing the universe at the earliest moments in the history of the universe. We're working on theories that combine gravity and quantum mechanics, but we're not there yet. But presumably, when you compress something to high enough densities, there are quantum mechanical effects. And the idea in cosmology is that there are quantum mechanical effects that are essentially random variations that are inflated to large scales, and these quantum mechanical oscillations, actually these ripples in space-time, end up becoming the seeds for galaxy and structure formation that we see today. You can sort of draw an analogy to a water droplet bouncing on the surface of water. Here you have the physics of gravity and surface tension governing how these systems evolve in time. But it's actually a little bit more complicated when you talk about a system that's composed of photons and baryons and dark matter, etc. But there are some nice analogies. So think of this as a quantum mechanical oscillation that is evolving in time. You actually have many of these in space-time, and they're interacting and leaving patterns in the surface of the liquid. And you know, you can zoom out and you can see a whole sea of these ripples. We can actually make computer simulations of these ripples, fluctuations in the energy content of the universe. And so what we have then is a cosmic fluid composed of dark matter, baryons, and photons that is interacting to some extent, either gravitationally or through the electromagnetic force. And you can look at to see how these water droplets or quantum dots, so to speak, evolve in time. And you know, actually, it turns out that gravity, dark matter and normal matter, baryons, interact gravitationally, and so you know, that's an important effect that we have to keep in mind. But normal matter also interacts with light, as we know. And so there are these interesting evolutions of shells that we can see when we run these simulations. We get interesting patterns, and these patterns are known as baryon acoustic oscillations. This is a single quantum perturbation, so to speak. We actually have many, and you can run simulations where you have many perturbations like these. And at the end of that simulation, you're left with some pattern that looks like these random variations in density. These are exactly the same random variations in density that we're seeing here. So it's by looking at the statistical properties of these variations and fitting models that describe the evolution of dark matter, dark energy, neutrinos, light, etc., that we're able to constrain the properties of the universe. Okay, I'm glossing over a lot of technical details. I'm not going to have time to talk about how we actually arrive at these beautiful images of the universe. For example, in the case of Planck, we have terabytes of raw data that we're compressing into a few 50 megapixel images. of the microwave sky at different frequencies, which then we actually compress even further into these so-called angular power spectra, which describe the variations in this primordial plasma as a function of a mysterious number that we refer to as a multiple moment. I even failed to label the axis, but this is actually can be mapped to angular scale. And these variations here are what we refer to as acoustic oscillations. And these have a perfect analogy to these ripples in the surface of liquid that I was showing earlier. These are sound waves in the primordial liquid, so to speak. And from this extreme data compression, we ultimately arrive at models of the universe, which we refer to as lambda CDM, which stands for dark energy, cold dark matter, and a little bit of baryons. And this is the energy, an energy budget of the universe that we estimate today. So that's sort of one way that you can think about this type of data analysis that we do in cosmic microwave background research. So when we explore the millimeter wavelength sky or the microwave sky, we can learn a lot about the earliest moments in the universe, in fact. We can learn more about dark matter and dark energy and ordinary matter. We can study neutrinos and the properties of neutrinos. We can learn about the birth of the first stars. And we can even search for a hypothesized planet 9. It turns out that, rather recently we've started to realize that there might be a cold, dark planet lurking somewhere in the Oort cloud, so outside the orbit of Neptune, pulling on the inner planets. And the comets and asteroids that live there. So we're actually conducting studies with data from microwave telescopes to search for this planet. So there's lots of things that we can learn more about the universe through the study of the CMB. So the story essentially goes like this. Quantum ripples at the beginning of time, it gets inflated up to the CMB anisotropies that we measure today with our telescopes, which then form the seeds for the formations of galaxies and galaxy clusters in deep gravitational wells where matter tends to cluster. Okay, so these primordial seeds that we imagine are put in place by early universe physics, they can actually also lead to polarization in the cosmic microwave background. So all these images that I've been showing so far have to do with the intensity, the non-polarized part of the light from the CMB. But it actually is the case that the CMB is partially polarized, and you can sort of see that by imagining that you're an electron in this primordial plasma, and you see a hot spot above you and below you, and a cold spot to the side, and then because these hot radiations and cold radiations shake the electron will oscillate and emit radiation that ends up becoming polarized. So we like to describe this polarization field that we see on the sky using so-called E-mode patterns and B-mode patterns. The E-mode patterns are symmetric around a mirror reflection. If I mirror this pattern around this plane here, it stays unaltered, whereas the B-mode patterns have a handedness. They actually, they change under reflection. So these patterns, it's kind of difficult to talk about why we decompose the polarization into these patterns. But it turns out that some ideas about cosmic inflation, some ideas about the earliest moments in the history of the universe predict that there's a pattern known as this B-mode polarization pattern, these swirly patterns, that is left over in the polarization of the CMB. We've detected this signal. This is much more mundane and produced by standard cosmology. These swirly patterns are something that we're still searching for. Okay, so this is actually, the search for this swirly pattern in the microwave sky actually reached the world news in 2014, not for a very good reason, unfortunately, but there was an announcement in 2014 saying that a group of scientists using the BICEP 2 telescope at the South Pole had detected this B-mode signal. Now, unfortunately, that was an error. They had misestimated the fact, or underestimated the fact, that we live in a galaxy and what that does to the signal. So this is an image that they published in 2014, a beautiful image showing these swirly patterns that I was mentioning earlier. And the claim was, at the time, that these swirly patterns could be linked to cosmic inflation, and we can actually say something about very early universe physics by measuring the amplitudes of these patterns. But we live in a galaxy. And the galaxy is beautiful. If you haven't had an opportunity to do this, I recommend going away from the light pollution of the cities and looking at the galactic plane. When you look closely at the galactic plane, you actually see these black clouds. This is dust and gas that absorbs radiation from the stars behind the gas. This is the same stuff that actually created that variation in the shape of the galaxy as estimated by William Herschel in 1785. This is also the stuff that's responsible for the mistakes or errors that were made in that paper in 2014. So when you look at images from the Planck satellite, which is the most recent satellite studying the cosmic microwave background, you have clear indication that there are these variations that we are very much interested in from the cosmic microwave background. But we live in a galaxy, and the galaxy is beautiful and it's complex, and it poses a problem to this particular type of research. So it turns out that supernovae, which expel matter, they actually, these stars in their end stages produce the heavy elements. The elements are not produced in primordial nuclear synthesis, carbon, oxygen, silicon, etc. Some of those elements end up becoming dust grains, galactic dust, micrometer-sized particles, which might look something like this. And these dust grains are actually, some of them are magnetic. They have a magnetic dipole moment, and they align themselves with the magnetic field in our galaxy. So our galaxy actually has a magnetic field. And this is, again, data from the Planck satellite showing estimates for what the shapes of those galactic magnetic field lines look like. And these dust grains actually have a characteristic temperature of about 20 Kelvin, and they radiate polarization into every direction. And we pick up that polarization. Some of that we assume is in the form of these swirly B-mode polarization patterns. So unfortunately, the BICEP2 collaboration had underestimated the impact of our own galaxy, and these swirly patterns that they detected can be attributed simply to interstellar dust. Okay, so this is a long story, and we can talk more about this effort, for many minutes, many hours. I'm just going to spend 3 or so minutes talking about one experiment that I worked on as part of my PhD, the Spider balloon-borne CMB polarimeter, which basically is a fancy word for an instrument that detects polarization. So this is an interesting experiment for many reasons. This is an image taken at McMurdo Station, which is the southernmost harbor in the world. We attach this telescope to a helium balloon. We launch it into the stratosphere to an altitude of about 35 kilometers. And we let the stratospheric winds move it around the South Pole, and we observe the sky while this instrument is airborne. So these are the balloonatics, the experimentalists that had the opportunity of going to Antarctica and to work on this instrument, and some of the organizations and universities that were associated. This is a really interesting experiment for a number of reasons. One of the cool things about these balloon-borne experiments is that they give a chance for young people, PhD students that are sort of starting to develop their expertise and skills in astrophysics to cut their teeth on something real, something that actually has an impact in astrophysics and cosmology. So most of this instrument that you see here is built by PhD students. It's a 3.5-ton machine, most sensitive microwave instrument to date, 15 kilometers of cryogenic wiring. All of this instrument here is under vacuum and cooled down to low temperatures so that the telescopes are sensitive to the very faint cosmic microwave background radiation. It's handmade with love most of the time. Right, so we launched from this place, McMurdo Station, and we circled the South Pole. We launched on January the 1st, 2015. Here are some of the reasons for actually in favor of ballooning. If you buy me a beer, I will tell you about some of the negative aspects of ballooning. So we launched on January 1st, 2015. We ended the flight on January 17, I think, at which point we separate our payload from the balloon. Our parachute opens up and it lands somewhere in Antarctica. And this is a picture taken on February 5th, 2015, showing the carcass that has landed there. We fly in, we have 2 individuals on a small plane, finding the payload, extracting the hard drives, and then leaving the Antarctic continent, because this is the time when winter is coming, and so basically we don't have the time to work on recovering this scientific payload. 6 months later we show up again, now in force with about 10 individuals, and we dig up this carcass and we remove it from the continent. A year later, this instrument that I worked on for my PhD is being turned into recycled aluminum somewhere in central New Jersey, while other components are safely back in the lab, where we can look and see if it's actually all these telescopes. And this is actually where the photons from the cosmic microwave background end up becoming absorbed and read out. And we produced interesting results that have been published in recent years, describing and helping us understand cosmic inflation and also cosmic dust or galactic dust. So these are some of the data results that came from that experiment. And we actually recovered or recycled part of the instrument and flew it again on the 22nd of December last year. So Spider 2 launched then and actually produced even more interesting data. So that's where I'm going to stop and say thank you. Yeah.
Thank you, Jon, for your excellent presentation. And time for questions, please.
Don't be shy.
I'd like to ask you then, how long the Spider 2 will stay? Or you say that it was launched in 2022?
Yeah, it was launched, it stayed up for about 10 days. So it's actually slightly shorter flight than the first flight. Part of it has to do with these telescopes have to be cooled down to sub-Kelvin temperatures, and the cryogen, the helium that is cooling the telescope, had run out at that point. Mm-hmm. So that's why that flight was ended.
And then related to that, you show that the Spider 1 was more or less getting better than the Planck. What you're suspecting here with Spider 2, you know, to get?
Well, I don't know if I have that slide somewhere.
Yeah.
But basically, we're probing different frequencies compared to the Planck satellite. Yeah, so we actually throw in a new frequency band at 280 gigahertz that fills in a gap between 2 of the frequencies that the Planck satellite mapped out. So we're trying to learn a lot about galactic dust, and this particular frequency band will help us learn more and adds to the information that we have from the Planck satellite. Yeah.
Questions? Yeah. I come to you.
Yeah. Thanks, Jon. So I guess a pair of questions. So first, How does the new spider run fit into the gaps in the literature? I guess you mentioned that briefly just now. Second, do you have any sense for how good the data is, or when we might see results from that? It's probably going to be a while, but so those two questions.
Yeah. Okay. Well, so I can't say anything about it. So it's very early days in data analysis. We launched Spider 2, a few months ago, and we're still just looking at the data. It's gonna, for Spider 1, it took us a few years to publish results. So I'm not allowed to say anything about the quality of data from Spider 2. I'm sorry. Now, I mean, this data set at 280 gigahertz is going to be quite valuable because it fills in this gap that we have in the data from the Planck satellite. So we don't actually know what we're going to see because nobody's actually conducted measurements at these frequencies before. So we'll see. Mm-hmm. Oh, the balloon. The balloon costs about a few $100,000. So it's not this instrument to build it is order $5 to $10 million. The balloon is a few $100,000. So it's expensive, and it's kind of surprising because the material that makes up these balloons is essentially HDPE plastic. It's the same type of plastic we used to use when we went to the grocery store, and it's really thin. But that's what these balloons are made out of. Yeah.
Questions? I'd like to ask you another question. Mm-hmm. I mean, now we are talking a lot about AI and how the data we learn from the previous data on learning and so on. Are these now this AI method could be used now to help you or for analyzing or predicting or something? I don't know. Yeah.
So in terms of analyzing these maps, we're starting to see some hints that we can use AI models to learn about, for example, galactic foregrounds and do this component separation where we subtract contributions from dust and contributions from synchrotron radiation, etc. I haven't yet seen a very strong motivation for using AI for these techniques, because in doing cosmological inference, in saying something about the properties of the universe, we need most of the time some kind of parameterized model that we understand. And the output of these AI models are models, but we don't really understand the models, so it's difficult to parameterize them, and it makes our analysis a little bit more complicated. But I think the verdict is still out. We don't know whether we can use AI for these types of data. Yeah.
More? Yeah, please.
Use the redshift of a galaxy far away to see how far away it is. That's a normal thing, I think. But some galaxies are moving towards each other. How?
Yeah, they're
how is that possible?
Well, actually, as you move further and further out into the universe, the galaxies all follow essentially the Hubble flow, and they're moving predominantly away from us. So the further out you look, the more likely it is that the galaxy is going to be moving away from you. It's going to be red-shifted as opposed to blue-shifted. However, when you look at close-by galaxies, some of them are actually moving in our direction. It's more likely that you'll find a galaxy that has a peculiar velocity in our direction.
I had the idea that everything was moving away from each other, but that's not true then.
Not 100% true, like the Andromeda galaxy, which is moving towards us, but it's close by. There are other galaxies that are moving in our direction. We see a blue shift in the spectrum, but as you look out to larger and larger, what we refer to as redshifts, to further and further distances, this goes away, and almost all the galaxies are moving away from us. So I can go back to this picture here. Oh wow.
Yes.
Hello. Hi. Just thought about this CMB maps and derivations of that.
Mhm.
It reminds me of a totally different type of maps in my field, oil exploration, where some specialists are quite good at filtering and enhancing those type of maps. Have you had, so the question is, have you had any collaboration with filter experts in other fields?
Gosh. So there's, I mean, I think it's fair to say that the techniques that we're using to extract information from these data are sort of, to some extent, they represent the state of the art. But that does not mean that theorists and people that are working in a data analysis regime are not trying different techniques and basically looking at all the tools that are in our collective arsenal to extract information about the CMB. So we use all sorts of data analysis, filtering techniques, both in producing, taking the raw data, these time streams that are produced by, for example, the Planck satellite, to compress those into images and maps, etc. Those algorithms that are being developed are, they're tested rigorously as part of developing essentially the final scientific results. So we're doing all sorts of tests on these algorithms to make sure that the algorithms themselves don't actually leave some kind of false signatures in the final scientific result.
I just wondered if totally disparate fields have.
Yeah, it happens. I think we should do more of this in science in general, to actually put two people from very different branches of science into the same room to work together and see how their different techniques and different ways of solving similar problems can benefit each other. So we're doing that more and more to some extent, but it's hard to say what kind of techniques would, for me to say what kind of different fields we should collaborate with. Yeah.
More questions? I have another question. You say that the universe now is accelerating.
Yes.
Right?
Yeah.
What means for the future? I mean, what something is accelerating, diverging, or I don't know what will happen.
Yeah. So this. So I mentioned Jim Peoples and the fact that he received the Nobel Prize. I think it was in 2019, just before COVID. And there's, as part of that award, there are documents that are written and published on the Nobel Prize website. And one of those documents, it's kind of not obvious, but when you look at one of the figures in that document, you can see when you extrapolate outwards, it suggests that the universe will continue to expand and accelerate in its expansion, and eventually die in what we refer to as a thermal heat death. So if we extrapolate the models that we have right now for the evolution of the universe, it's going to accelerate in its expansion. The stars will eventually, and the galaxies will eventually separate completely, and eventually those last remaining stars will dwindle. So that's one prediction. We don't know anything about dark matter. We don't know anything about dark energy. So it's extrapolating out to infinity. To me, feels like a bit of a reach. But that's what we get when we do that extrapolation. Yeah.
More questions? I see no hands. No. Okay. I'd like to thank Jon for excellent presentation and excellent lecture.